When calculating the total volt amps load for service supplying multiple motors with different voltage ratings, it is important to consider several factors. These include the type of motors, their voltage ratings, whether they operate continuously or intermittently, and the applicable electrical codes. For single-phase motors, the volt amps are calculated by multiplying the current in amps by the voltage. For three-phase motors, the volt amps are calculated by multiplying the current in amps by the voltage and then by the square root of 3, which is approximately 1.732. Always use the nameplate voltage for all motor calculations. This is the voltage specified on the motor's nameplate, not necessarily the input voltage of the service. When dealing with intermittent duty motors, if they are not operating continuously, you can ignore the duty rating. This simplifies the calculations, as you do not need to apply any additional demand factors based on the duty cycle. In the calculation, firstly, calculate the volt amps for each of the 115/230 volts motors. This involves multiplying the nameplate current of each motor by its respective voltage. For motor number 1, with a nameplate current of 19.92 amps and a voltage of 115 volts, the volt amps are 19.92 amps times 115 volts, which equals 2291 volt amps. For motor number 2, with a nameplate current of 28.22 amps and a voltage of 115 volts, the volt amps are 28.22 amps times 115 volts, which equals 3235 volt amps. For motor number 3, with a nameplate current of 23.24 amps and a voltage of 230 volts, the volt amps are 23.24 amps times 230 volts, which equals 5343 volt amps. Then, add up the volt amps for all the 115/230 volts motors. The total volt amps for the 115/230 volts motors is 2291 volt amps plus 3235 volt amps plus 5343 volt amps, which equals 10,869 volt amps. Secondly, calculate the volt amps for each of the 460 volts motors. For motor number 4, with a nameplate current of 33.2 amps and a voltage of 460 volts, the volt amps are 33.2 amps times 460 volts, which equals 15,232 volt amps. For motor number 5, with a nameplate current of 43.16 amps and a voltage of 460 volts, the volt amps are 43.16 amps times 460 volts, which equals 19,958 volt amps. For motor number 6, with a nameplate current of 53.95 amps and a voltage of 460 volts, the volt amps are 53.95 amps times 460 volts, which equals 24,858 volt amps. Next, add up the volt amps for all the 460 volts motors. The total volt amps for the 460 volts motors is 15,232 volt amps plus 19,958 volt amps plus 24,858 volt amps, which equals 60,048 volt amps. Thirdly, calculate the total service load volt amps. To find the total service load volt amps, add the total volt amps of the 115/230 volts motors to the total volt amps of the 460 volts motors. The total service load volt amps is 10,869 volt amps plus 60,048 volt amps, which equals 70,917 volt amps. Therefore, the load on the service is 70,917 volt amps. This is an important step in electrical service design and ensures that the system can safely and effectively handle the connected loads. It's important to remember a few key concepts. Firstly, always use nameplate voltage values for accurate calculations. Secondly, ignore the duty rating for intermittent motors unless they operate continuously. Thirdly, accurately calculate volt amps for both single-phase and three-phase motors using the appropriate formulas. Also, ensure you are adhering to the National Electrical Code, or NEC, Guidelines for motor circuit calculations. This code provides standards for electrical safety and proper installation methods. One of the requirements in Article 430 of the NEC is motor circuit conductors. The ampacity of conductors supplying a single motor used for continuous duty must have an ampacity of not less than 125% of the motor's full load current as determined by the motor's nameplate rating. For example, if you have a motor with a full load current rating of 20 amps and is used for continuous duty, the conductors supplying this motor must have an ampacity of at least 25 amps, which is 20 amps times 1.25. In situations where a motor is used for short time, intermittent, periodic, or varying duty, the conductor's ampacity is based on the duty cycle. Motors used for these types of duty usually operate at intervals, not continuously. In these cases, the NEC allows for the use of a demand factor to reduce the required conductor ampacity. For example, if the duty cycle is 50%, the demand factor is 0.5. If the duty cycle is 25%, the demand factor is 0.25. The motor full load current is multiplied by this demand factor to determine the required conductor ampacity. Article 430.24 of the NEC covers the ampacity of conductors supplying several motors. This is applicable where two or more motors are supplied by a single set of conductors. The conductor ampacity must not be less than 125% of the full load current rating of the highest rated motor, plus the sum of the full load current ratings of all other motors in the group. For example, if you have a group of motors and the highest rated motor has a full load current of 20 amps, and the other motors have full load currents of 10 amps, 8 amps, and 5 amps, the required conductor ampacity would be 25 amps, which is 20 amps times 1.25, plus 10 amps plus 8 amps plus 5 amps, which equals 48 amps. Article 430.52 covers motor circuit protection. Each motor must be protected against overcurrent, overload, and short circuits. Overcurrent protection is typically provided by fuses or circuit breakers. Overload protection is typically provided by thermal overload relays. The size of the overcurrent protection device must be selected based on the full load current rating of the motor. The overload protection device must be selected based on the motor's service factor and temperature rise. For example, according to NEC Table 430.52, the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices for inverse time circuit breakers is typically 250% of the motor's full load current. For fuses, it ranges from 175 to 300% depending on the type. When sizing a transformer for motor loads, it is essential to follow the guidelines provided in Article 450 of the NEC. Firstly, determine the total volt-ampere, or VAR, load of all the motors that the transformer will supply. This involves summing up the volt-ampere ratings of each motor, taking into account their individual characteristics such as horsepower, voltage, and full load current. For example, if you have several motors with different horsepower and voltage ratings, you need to convert each motor's specifications into volt-amperes. A 10 horsepower motor operating at 480 volts will have a different volt-ampere rating than a 5 horsepower motor operating at 240 volts. You use the formula volt-amperes equals volts times amps for single-phase loads, or volt-amperes equals volts times amps times the square root of 3 for three-phase loads. Secondly, apply any applicable demand factors. Demand factors are used to account for the fact that not all motors will operate at their full load capacity simultaneously. The NEC allows the use of demand factors based on the type of load and the expected duty cycle. If all motors are expected to operate simultaneously at full load, a demand factor of 1.0 is used. If it is known that only a percentage of the motors will operate at any given time, a lower demand factor can be applied. For example, if it is estimated that only 80% of the motors will operate at the same time, a demand factor of 0.8 can be used. Thirdly, select a transformer with a volt-ampere rating that is equal to or greater than the calculated load. It is important to select a transformer with adequate capacity to handle the motor loads without being overloaded. Transformers are typically rated in kV amperes, so you may need to convert the total volt-ampere load into kV amperes by dividing by 1000. For example, if the total volt-ampere load is 75,000 volt-amperes, this is equivalent to 75 kV amperes. You would select a transformer with a rating of at least 75 kV amperes. Also, consider future expansion. When selecting a transformer, it is advisable to consider future load growth. Selecting a transformer with a slightly higher capacity than currently needed can accommodate additional motor loads in the future. For example, if you anticipate adding more motors in the future, you might select a transformer with a capacity that is 25% higher than the current load requirement. Inrush current must also be considered. Motor starting inrush current can be several times higher than the motor's full load current. This inrush current can cause voltage dips and can potentially overload the transformer. To address this issue, you may need to select a transformer with a higher kV ampere rating or use soft starters or variable frequency drives to limit the inrush current. For example, if a motor has an inrush current that is 6 times its full load current, you might need to select a transformer with a kV ampere rating that is sufficient to handle this inrush current without causing excessive voltage drops. Also, it's important to ensure compliance with NEC standards. When sizing a transformer for motor loads, it is important to comply with the relevant articles of the NEC, specifically Article 450, which provides requirements for transformer installations. Article 430 covers motor circuits and overload protection. These articles provide guidelines for overcurrent protection, conductor sizing, and other important considerations. For example, the NEC specifies the maximum overcurrent protection device size for transformers based on their kV ampere rating and voltage.